Hi, continuity part 3. So in this session I am going to discuss types of discontinuity. So there are two types of discontinuities. The first type is removable discontinuity. In this type, limit of the function is exist. Next, second type, non-removable discontinuity. In this second type, limit does not exist. Now, again in first type there are two things are there. Again the first type is in first type again we have two things. So in removable discontinuity we have two types. Okay. Type 1 missing point discontinuity. Type 2 isolated point discontinuity. In non-removable discontinuity there are three types: finite type, infinite type, oscillatory type. Okay. Now in removable discontinuity, what is the missing point discontinuity? What is the missing point discontinuity? So from this definition over here we have a missing point discontinuity. So graph will be like this. So what do you say now from this graph? The limit of the function exists at a, but the function is not defined at a. The limit of the function exists at a, but the value of the function does not exist at a. The f of a is not exist, but limit of the function at a exists. For this examples, f of x is equal to sin x by x at x is equal to 0. In missing point type continuity, so one example, f of x is equal to sin x by x at x is equal to 0. See now limit extends to 0, sin x by x is what? 1. So limit is exist. Limit of this function is exist. But what is f of 0? Sin 0, 0, 0 by 0. So f of 0 is not defined. So it is an example for missing point discontinuity. Next one more example, f of x is equal to x square minus 1 by x minus 1 at x is equal to 1. So if you find limit extends to 1 of this function, second function, limit extends to 1 f of x, you will get 2. Okay. But if you find f of 1, what you will get? 1 minus 1, 0 by 0. So f of 1 is not defined. F of 1 does not exist. So that means in these two examples, the limit of the function exists, but the value of the function does not exist. So this function has missing point discontinuity at 0. This function has missing point discontinuity at 1. Okay. Next to isolated point discontinuity. Isolated point discontinuity. So coming to this isolated point discontinuity means you will get the graph will be like this. See here limit of the function is exist and f of a is also exist, but limit not equal to value of the function. Both limit of the function and value of the function both are exist, but they are not equal. For example, f of x is equal to x square minus 9 by x minus 3 for x not equal to 3 and its value 7 for x is equal to 3. So you find the limit of the function at 3 at x is equal to 3. So at x is equal to 3, the function has, this function f of x has isolated point discontinuity. Because if you find limit of the function at 3, you will get 6, but the value of the function is 7. Both are exist, but they are not equal. Even you can give your own examples also. I suppose if I take f of x is equal to x for x is not equal to 3 and its value is 5 for x is equal to 3. So the value of the function at 3 is 5. If you find limit of the function at 3, what do you get? 3. So these are the some examples. These are the some examples for isolated point discontinuity. In missing point and isolated point discontinuity, in both cases, the function has removable. The function is said to be has removable. In both cases, we can remove the discontinuity of the function. How we can remove? By redefining the value of the function same as limit of the function. then we can make such functions as continuous functions. That is why that such kind of discontinuity is called removable discontinuity. So why we call these two are removable discontinuity? In both cases it is possible to remove the discontinuity of the function by redefining the value of the function is same as limit of the function. Suppose if I redefine this function as f of x is equal to x for x not equal to 3 and its value 3 for x is equal to 3. So if I redefine this function as like this, so that the function is continuous. That is why in both cases the function has what? Removable discontinuity. Next, non-removable discontinuity. That means in that case it is not possible to remove the discontinuity of the function at given points. So in this case, in all three cases, common point is what? Limit does not exist. Limit does not exist. So coming to the non-removable discontinuity, in that limit does not exist. In that first type, finite type. So in this first type, both LHL and RHL, are exist and finite. Exist and finite. But they are not equal. Both LHL and RHL are exist and finite, but they are not equal. So limit does not exist, hence the function has non-removable discontinuity. And in this case, the difference between, the positive difference between LHL and RHL, whatever you will get some quantity, some finite quantity, that finite quantity is called jump. That is called jump of discontinuity. That is called jump of discontinuity of f. Whatever you will get some finite quantity, that finite quantity is what? Jump of discontinuity of f. Okay. So for example, if you take f of x is equal to step x at any integral points, say at x is equal to 3, and if you find left hand limit for this function, you will get 2, and if you find right hand limit for this function 3, see both are exist and finite. And what is the difference between LHL to RHL? It is 1. That means here the graph of the function, after 3 it will jump 1 unit either above or 1 unit below. If RHL value is more, here RHL value is more, then 1 unit above. After 3, from if you go the graph of the function, if you go along the graph of this function at the point 3, from left side of 3 to right side of 3, the graph of the function will jump 1 unit above because RHL is more. Suppose if LHL is more, suppose you got LHL, say LHL, suppose you got 10, RHL you got suppose 5. So what is the difference between 10 and 5? 5. So that means after that point, the graph of the function will jump 5 units below, because here RHL value is less. If RHL value is less, so whatever you got this difference, okay, that much of units will go down. If RHL value is more, so whatever you will get this quantity, that much of units go up. Okay. So in this example, at 3, if you go from left side of 3 to right side of 3, the graph will jump 1 unit above. Okay. And this one is called what? Jump of discontinuity of this function at the point 3. And also, if you take suppose a function, say f of x, if f of x has a finite number of jumps, if a function has finite number of jumps in a given interval I, then we say that the function is piecewise continuous function on I, or sectionally continuous function on I. If f of x has finite number of jumps in a given interval, finite number of jumps, jumps, okay, in a given interval I, then we say that the function is a piecewise continuous function on I, or sectionally continuous function on capital I. Example, you can take even tan x, cot x, secant x, cosecant x. All these functions are piecewise continuous functions. Okay. Next, coming to the infinite type. Infinite type. Infinite type. So here LHL, RHL, at least one of these, at least one of LHL, RHL is infinite. Is infinity. At least one of LHL, RHL is infinity, infinite. It may be plus infinite or minus infinite. For example, if you take f of x is equal to 1 by x at x is equal to 0, you will get LHL is when extending to 0 minus 1 by x is tending to minus infinity. When extending to 0 plus RHL, when extending to 0 plus 1 by x tending to what? Plus infinity. Okay. So in this case, the function has non-removable discontinuity at 0, particularly which type? Infinite type. Next, one more example. F of x is equal to 2 power tan x at x is equal to pi by 2. At x is equal to pi by 2. If you find LHL, when extending to pi by 2 minus tan x tending to plus infinity, 2 power infinity is infinite. So when extending to pi by 2 plus second quadrant, tan x tending to infinite. Which infinite? Minus infinite. 2 power minus infinity is 1 by 2 power infinity. 1 by 2 power infinity is 1 by infinity. 1 by infinity is what? 0. So 2 power tan x has infinite type discontinuity at x is equal to pi by 2. Not only pi by 2, at all odd multiples of pi by 2. Next to example, f of x is equal to 1 upon x minus 1 whole square at x is equal to 1. So for this function, both LHL, RHL are equal to infinity. Both LHL and RHL are equal to what? Infinity. Because when extending to 1 plus or 1 minus, x minus 1 whole square is tending to 0 plus. 1 upon 0 plus is infinity. Okay. Next to oscillatory type. Last type, oscillatory type. So when we say that a function has oscillatory type discontinuity at a given point, if third one, if limits oscillate, third type, if limits oscillate between two finite quantities. So when we say that a function has oscillatory type of discontinuity, if the limits at those points, at that point or at those points oscillate between two finite quantities. Okay. If the limit of the function at those points oscillating between two finite quantities, then we say that the function has oscillatory type discontinuity. For example, if you take f of x is equal to sine 1 by x or cos 1 by x at x is equal to 0, these functions have oscillatory type of discontinuity because these two functions are oscillates between minus 1 and plus 1. These two functions are at 0, they are oscillating between minus 1 and plus 1. Next to One more example. If you take a f of x is equal to step of integral part of 1 plus sine of log of mod x at x is equal to 0. This function also having oscillates between 0 and 2. This function also oscillates between 0 and 2 at x is equal to 0. Okay, so at x is equal to 0, this function is also oscillating between 0 and 2, and I think it is not step. Yeah, it is not step function. It is normal. Okay, 1 plus sine of ln of mod x, it is oscillating between 0 and 2 at x is equal to 0. Okay. Next. So these are the types of discontinuity. Okay. Missing point, isolated point, removable. Finite type, infinite type, oscillator type is non-removable. Removable, in removable, limit is exist. In non-removable, limit does not exist. Okay. So this concept is exclusively useful for you advanced level. Even in mains level also they are not asking the problems based on these types. Okay. Next, find the number of points of discontinuity of following functions. Just we have to find number of points of discontinuity. The first problem is given f of x is equal to 1 by log of mod x with base e. So we know that log of mod x function is continuous everywhere except at the points where it is not defined. That means it is a continuous function. But 1 upon log mod x is also a continuous function. Log mod x function is continuous and 1 upon log mod x is also continuous function. So continuous function means what? It is continuous at every point in its domain. That means this function is continuous only in its domain. It is discontinuous at the points where it is not defined. So clearly this function is not defined when log of mod x is equal to 0 and mod x is equal to 0. So mod x is equal to 0 implies that what you will get x is equal to 0. Log of mod x is equal to 0 means mod x value must be equal to 1. So x is equal to plus or minus 1. So thus the points of discontinuity of this function is minus 1, 0, 1. And how many points are there? Total 3 points. Minus 1, 0 and 1. Next, f of x is equal to 1 upon x minus 1. So it is a rational function. It is defined only in its domain. So this is discontinuous when denominator is 0. So x minus 1 is 0. So thus what you will get x value? 1. And also when extending to 1 plus. So also if you find LHL you will get minus infinity. RHL at 1 what you will get? Plus infinity. So it is discontinuous at x is equal to 1 only. So number of points of discontinuity is 1. And it is what type of discontinuity I am finding. So LHL what I got? Minus infinity. RHL what I got? Plus infinity. So that means at x is equal to 1 function has non-removable discontinuity because LHL not equal to RHL, limit does not exist. And both are tending to what? Infinite. So that means it is a non-removable discontinuity only. What type discontinuity is? Infinite type discontinuity. Okay. Next problem. F of x is equal to modulus of x minus 1 by x minus 1. So clearly if you find LHL when extending to 1 minus, mod x minus 1 is minus of x minus 1. So minus of x minus 1 by x minus 1 what do you get? Minus 1 because as extends to 1 minus x minus 1 is tending to what? 0 minus. That means x minus 1 is negative. So in that case mod x minus 1 is same as minus of x minus 1. So minus of x minus 1 by x minus 1 what you will get? Minus 1. So what you will get RHL? That means when extending to 1 plus x minus 1 tending to what? 0 plus. That means x minus 1 positive. Then mod x minus 1 is what? X minus 1. So x minus 1 by x minus 1, what do you get? Plus 1. So it is discontinuous at x is equal to 1. So mod x minus 1 by x minus 1 is discontinuous at x is equal to 1. So number of points of discontinuity is only 1. And here limit, is it exist? Does not exist, so non-removable. And it is finite type or infinite type? Finite type. And what is the jump of discontinuity? What is the difference between LHL and RHL? 2. The difference between LHL and RHL is what? LHL minus RHL. Modulus of LHL minus RHL, what will you get? 2. That means while going through this graph of the function at 1, from left side of 1 to right side of 1, the graph is jumped 2 units. Okay? 2 units above, because right hand limit is more. Next problem. So this is a exemplar book. Even in exemplar book also this problem is there, this model. X cube minus x by x square minus 1. So clearly this function is not defined when x square minus 1 is equal to 0. That is x is equal to plus or minus 1. That means this function is not defined at x is equal to plus or minus 1. Hence it is discontinuous at 1 and minus 1. And also, if you take x common in the numerator, what you will get? X square minus 1 divided by x square minus 1. So x square minus 1 and x square minus 1 get cancelled. So thus f of x is equal to x. Sir, it is an identity function, it is continuous everywhere. No. So when we can cancel these two? If it is not 0. So when it is not equal to 0? When x is not equal to plus or minus 1. That means f of x is equal to what? X when x is not equal to plus or minus 1. And at 1 if you find, limit of the function is exist. At minus 1 also limit of the function is exist. But the function is not defined at 1 and minus 1. So the limit of the function at 1 and minus 1 are exist. But the function is not defined at 1 and minus 1. That means at these 2 points, limit of the function exists, but the value of the function does not exist. So that means it is removable. Removable what? Missing type discontinuity. Missing type discontinuity. Next. Next, last problem. F of x is equal to sine of 1 by x minus 1. So clearly this function is not defined at x is equal to 1. Am I correct? Yes. So the function is discontinuous at 1. And what type of discontinuity this function has? So when x tending to 1, x minus 1 tending to what? 0. 1 upon x minus 1 tending to what? Plus infinity or minus infinity. Sine of tending to plus or minus infinity is an oscillating number between minus 1 and plus 1. So that means when x tending to 1, this function is oscillating between two finite quantities which are minus 1 and plus 1. So at x is equal to 1, this function has oscillatory type discontinuity, which is a non-removable and oscillatory type discontinuity. Okay. Next, some theorems on continuity. So, some theorem. So, this theorem is there even in theory also. If f and g both are continuous at x is equal to a, if f and g both are continuous at x is equal to a, then f plus g, f minus g, f into g are also continuous at x is equal to a. Okay, and f by g is continuous at x is equal to a, is continuous at x is equal to a only if g of a not equal to 0. Because g of a means it is g function is denominator now, it should not be equal to 0. If it is 0, then f by g function is not continuous at a, even though f and g are continuous at a. Next to some important points. If f is continuous function and g is a discontinuous function, then f plus g is always discontinuous. Remember? So the combination, the linear combination of a continuous and a discontinuous function is always discontinuous function. Okay? The linear combination of a continuous and discontinuous function is always discontinuous. Simply remember, if f is continuous, g is discontinuous, f plus g is always discontinuous. Okay? Next, if f is continuous, g is discontinuous, then f into g need not be discontinuous. So for example, if I take f of x is equal to x and g of x is equal to sine 1 by x for x not equal to 0 and is 0 when x is equal to 0. See, this function is continuous at 0, but this function is not continuous at 0. But f of x into g of x function, it is continuous at 0. It is continuous at x is equal to 0. That means a product of a continuous and discontinuous function need not be discontinuous. And also, if f and g both are discontinuous, even though the product need not be discontinuous. Okay? Here in this case, one is continuous, other one is not continuous, but product is may be continuous, may not be continuous. Similarly, if both are discontinuous also, the function may be continuous, may not be continuous. So it is not necessary that it is always discontinuous. Okay? If f and g both are discontinuous, for example, if I define f of x is equal to 1 for x less than or equal to 0, minus 1 for x greater than or equal to 0, for x greater than 0, and gx function as like this 2 when x less than or equal to 0 and minus 2 for x greater than 0. If you observe, both f and g are discontinuous at 0. But if you find f of x into g of x, you will get 2 for all x. So constant function continuous. So f discontinuous at 0, g discontinuous at 0, fx into gx is a constant, it is a continuous everywhere. In particular, it is continuous at 0 also. So thank you.